Good morning and welcome to the lecture number 37 of the course Water Resource Systems, Modeling Techniques and Analysis. Over the last few lectures, we have discussed the fuzzy optimization technique, which is especially useful when there is a conflict in the water resource systems, which typically exists because there are several stakeholders in any water resource systems problem. Specifically, what we dealt with in the previous lecture, that is the last lecture, was to deal with a situation where we have a storage target and a demand and the release target. And these two are conflicting in general, because if you make more release, then the storage will be depleted. So, if you want to maintain both the storage target as well as the release target, one way of doing that was through our deterministic crisp optimization, where you will take the minimized squared deficit like this and then penalize the T s itself. Here T s is the storage target and you were maximizing the storage target, and that is how you you obtain the maximized storage target and the associated storages during each of the time periods for a given inflow sequence, and this also decides on the releases for a given k, that is a storage capacity. And then you are looking at the deviations of the release from the target, that is a only whenever there is a deficit release from the target. So, this was your crisp problem. This you converted into a fuzzy optimization problem by defining fuzzy membership function for the storage as well as for the release. Now, for the storage, what did we do? We said as it approaches, as the storage S t during time period t approaches the storage target T s, which is again a decision variable, then the membership function becomes closer to 1. As it deviates away from T s, the membership function will be closer to 0 on either side of T s. Whereas, on the release, what we said is that if the release is greater than the T r, our membership function is 1. Now, we constructed these membership functions and then looked at looked at the objective function, where we are maximizing the minimum of these membership functions mu s t and mu r t. So, the decisions are s t and r t, and the associated membership functions are mu s t and mu r t. We are looking at that set of s t and r t which satisfies all these conditions, which will in fact maximize the minimum value associated with those particular membership functions mu s t and mu r t. So, this is the way we formulated the fuzzy optimization problem. We looked also at the comparison of solutions that we obtain from fuzzy optimization problem with crisp optimization problem for another example problem. So, with that, now we more or less complete the techniques that we have to learn for water resource systems analysis. So, right from beginning, if you recall, we have been focusing on the techniques of problem solutions. For example, we started with constrained and unconstrained optimization using the methods of calculus. Then we went on to the linear programming, and then the dynamic programming, simulation we covered, and then after that we went into probabilistic optimization problems or the stochastic optimization problems, where we dealt with chance constrained linear programming as well as stochastic dynamic programming. Then towards the end, I have introduced the fuzzy optimization problem. Now, these are essentially the techniques or the tools with which we address the problems, and as we have gone along, we have also dealt with reservoir operation problems, multi-reservoir operation problems, and water quality problem in the fuzzy optimization and so on. So, some of the applications we have dealt with, but the main focus was all through on the techniques themselves. So, from this lecture onwards, what we will do is, over the next 4 lectures including today's, we will take up some specific model formulations for specific problems dealing with water resources systems. In the process, I will also discuss some case studies, but the emphasis again is on model formulations using the techniques that we have gone through in this particular course. So, in today's lecture, we will introduce the important model formulation for conjunctive use of surface and groundwater. Now, this is we are talking about specifically large river basins or large water resource systems, where there is a source of surface water available, there is a source of groundwater available. You need to manage both these systems, groundwater system as well as surface water system together or conjunctively, such that you are able to meet the demands that are necessary, yet at the same time the system is sustainable, in the sense that the groundwaters do not deplete beyond a certain level. At the same time, the groundwater does not enter into the root zone, or it does not come nearer to the ground surface, causing salinity problems, waterlogging problems, etc. And in the deficit situation of surface water, you are able to use the groundwater to meet the demands. So, groundwater and surface water together you need to plan utilization of groundwater as well as surface water over a period of time. Now, this is extremely relevant in countries like ours, where there are large number of regions which receive deficit rainfall in many years, and then we need to use the groundwater resources during the deficit rainfall period, and at the same time recharge the groundwater whenever there is a excess rainfall. So, these two together, that is groundwater system as well as surface water system, we need to look at a joint or conjunctive use of both these resources together. Now, the type of model that I will introduce is extremely simple and the first cut type of model, just to understand how we formulate the models for such problems. It can in fact be as complex as the details that you would like to input into the model, which I will presently discuss. But because this is the first time I am talking about conjunctive use, let us just look at some physical features of the conjunctive use problem, and then see what are the advantages, what are the types of constraints that we need to meet, and so on. So, what does conjunctive use imply? It implies, first of all, we impound the stream water in a surface reservoir, and then we transfer this surface water at some optimum rate to the groundwater reservoir. So, we are meeting the demand, yet at the same time we are also recharging the groundwater. Then whenever there is a above normal precipitation, we use the surface water to the extent possible to meet the demands, and then the excess water we use to recharge the groundwater. We may have artificial recharge structures through which we recharge the groundwater. And then during the drought periods, where there is deficit rainfall, you have a large amount of groundwater storage available, which has been recharged during the excess rainfall period, and we start using the groundwater during the deficit period. So, groundwater actually is a sort of insurance against the droughts, and therefore, we need to look at the groundwater as a reserve storage, in which we keep on putting additional water that is available from the surface sources whenever there is a excess rainfall or excess surface water available. Now, during the drought period, what happens? Because you do not have surface water resources, you start using more of groundwater resources, and therefore, the groundwater starts depleting. Now, when we are operating the groundwater system in conjunction with the surface water system, we need to make sure that the groundwater levels will fluctuate within an acceptable band. That means, they should not cross an upper limit, because that will cause waterlogging. They should not cross a lower limit, that becomes unsustainable, because the groundwater levels will be lower to extents beyond possible usage. Then you must also realize here that the surface water reservoirs, once they are silted up, typically in the period of about 100 years or 150 years in some cases, the surface water reservoirs get silted up. Then you need to look for alternate surface water sources, whereas the groundwater storage by and large is stable. It is not dependent on how the development is taking place on the surface of the ground. The groundwater storage is more or less fixed for a particular region. So, yield from groundwater sources is therefore more dependable than that from surface reservoirs. If you are able to manage the groundwater resources well, you can depend more on the that is the reliability of groundwater supply can be increased. Also, the physical and chemical quality of groundwater is more uniform than that of surface water. Now, these are some of the advantages. However, in the coastal regions typically, if there is a saline groundwater, that is salinity ingress takes place and therefore, the groundwater becomes saline, in which case you need to inject more of fresh water or more of surface water, so that the salinity gets reduced. Now, of course, it is not practically possible to divert all of surface water to underground, even if the operation were profitable. What I mean by that is that you have a surface water source and then you may have certain means or mechanism by which you want to put the fresh water into the groundwater, but all of the surface water cannot obviously be put into the groundwater because of several constraints. Now, you look at a irrigated area. Typically, when we are talking about conjunctive use of surface and groundwater, especially in our country, we talk about irrigation, use of water for agriculture, which is irrigated agriculture. But this needs to be looked at in a slightly broader context also. Now, with water being used more in the urban areas, especially the groundwater being used more in the urban areas, it is important for us to look at conjunctive use of surface as well as groundwater sources in urban context also. But as far as this course is concerned, this lecture is concerned, I will focus mostly on the use of ground as well as surface water for irrigated agriculture. So, typically we have an irrigated area, you may have bore wells or tube wells from which you are using the groundwater. In addition, you may be supplying the water through surface source. For example, this is a canal and from the canal you have branch canals and the field canals, etc. So, you have a canal network also supplying water from the surface sources. You need to decide how many such wells are necessary in this irrigated area and what is the level of pumping that you need to do from each of these wells across each time period within a year, such that along with the surface water source, you are able to meet the demands to the best extent possible. So, that is the decision that you need to make. So, the question is how much of surface water and how much of groundwater we need to apply, such that this system becomes sustainable in the long run. Now, what do we mean by sustainability, etc.? We will slightly defer the discussion, but essentially it means that we are able to maintain this level of irrigation by using surface water and groundwater optimally over a long period of time. So, that is the idea. So, for a long period of time, we should be able to meet these demands satisfactorily. Now, during the excess period, I just mentioned that you may divert the excess rainfall or excess surface water into detention ponds. So, you may create some artificial detention ponds and divert this water, so that the water seeps through and then adds to the water table. In the conjunctive use, we must also be alert to the undesirable effects of excess use of groundwater or lowered use of groundwater, which will bring the groundwater to near surface. So, there are two issues that you need to keep in mind, especially when you are dealing with large irrigated areas. If you do not at all use the groundwater and simply you are using the surface water, from the surface water irrigation, there is a recharge that is taking place to the groundwater. As the water flows through the canals, there is a seepage and part of the seepage, in fact, most of the seepage may contribute to the groundwater, as the result of which the groundwater levels will be continuously increasing if you do not use the groundwater at all. And then the groundwater may enter into the root zone of the crops, because we are talking about the agriculture that is the irrigated agriculture. Once the groundwater enters the root zone, it causes salinity problems, water logging problems, etc., which affects the irrigation. And therefore, you need to manage the groundwater as well as the surface water systems, such that the ill effects are nullified or ill effects are taken care of. So, salination is one of the effects that you need to be alert. Then increased operation costs. What do we mean by this? Is that if you were only putting the surface water systems, then there is a initial capital cost for creating the infrastructure, but the operational cost will be minimal, because the water flows by gravity, and once the infrastructure is in place, you do not have to do much about the surface water systems. Whereas, if you want to develop the groundwater, you need to have energy costs associated with the groundwater usage. So, there is a increased operational cost if you start using groundwater. Then there is a danger of overdraft of groundwater basins. So, we need to look at all of these when we are looking at the conjunctive use of surface water and groundwater. Now, for the systems models, when we are looking at the conjunctive use of surface and groundwaters, we may have several objectives. For example, the first level of objective that we may want to formulate is to meet the water demands at lowest overall cost. So, you want to create a surface water infrastructure and you want to create a groundwater infrastructure to meet a certain demand pattern, and this infrastructure that you create along with the operational cost must be minimum, at the same time you should be able to meet the demands. That is the first level of objective. Then you may have several other objectives associated with the conjunctive use problem. For example, you may have a water quality objective, where you may want to maintain the concentration levels of water quality constituents, both in the surface water as well as in groundwater. So, you may have quality objectives which can be met through, which can be studied through the systems models. Then, as I just mentioned, there may be undesirable effects. Overdraft of groundwater levels should be discouraged or should be avoided. Then salinity should be avoided, or salinity should be minimized by using the surface water, which is the fresh water, into the groundwater. That means, you dilute the groundwater with the surface water, so that the salinity levels decrease. Then water logging, where the groundwater level rises to near ground surface, this should be avoided. So, these are some of the objectives that we need to look at. Now, whatever I just mentioned, this picture represents that. Let us say this is the agriculture area in which you are growing certain types of crops, let us say wheat or paddy or some other crops like this, maize and things like that. Now, this crops here will have a root zone like this, the effective root zone. By root zone, I mean the zone of soil below the crop from which the crops can extract water. So, in general, the root zone will be, the effective root zone will be more than the physical root length that the crops have, because the crops can suck water from this particular soil, which may be more than the physical length of the root itself. Now, if you do not use the groundwater correctly, what may happen is the groundwater table may keep on rising and then enter the root zone. So, this is the groundwater table. So, it may enter the root zone. Now, this causes the problem of water logging. However, if you keep on lowering the groundwater table, that means, if you keep on exploiting the groundwater without properly recharging it, then what happens is the groundwater table goes so below the ground level that it becomes unsustainable or unusable. So, this causes overdraft of the groundwater. So, we may want to have the water level or the groundwater table to fluctuate within certain band. It has to be below the root zone, and at the same time it should not go below certain specified water levels. So, we may specify desired level of groundwater or desired band within which the groundwater can fluctuate. With that background now, we will see how we formulate simple systems models for conjunctive use of surface and groundwater. So, typically you will have a surface source, you may have several surface sources, but the surface source may consist of a surface reservoir. There may be a dam with a canal network and so on. So, you have a surface reservoir. So, you will require the surface water resources data. These will include reservoir details, for example, all the salient features of the reservoir, the area capacity relationship and the height of the dam, the type of canal network and so on. Then you need the hydrology at that point, including the inflow, evaporation, seepage losses and so on. The complete hydrology is what is required. Similarly, at the groundwater, you may need the type of aquifer, you may need the boundaries of the aquifer, then aquifer parameters, typically the storage coefficient and the transmissivity, and you may need a calibrated groundwater model, because you are now talking about conjunctive use of surface as well as groundwater, and there is a continuous interaction. So, groundwater has its own flow mechanism, you need to be able to model the groundwater flow, and the surface water has its own hydrology, and that hydrology needs to be modeled. Then you need to know the geologic condition, because you are also talking about the recharge that adds to the groundwater, and therefore, the geologic conditions are important. Then water distribution system, both for surface water as well as for the groundwater, how many wells are there, what type of wells, what locations of wells and so on. And then of course, the water use pattern. This depends on the cropping pattern and what type of crop is grown, what is the crop calendar and what is the evapotranspirative demands of the crops and so on. So, all of these information will be necessary for getting a good model on surface and groundwater conjunctive use. Now, assuming that all of this information is available, what we will now do is, we will take a simple case of one surface reservoir and one groundwater reservoir. Together we will see how there is an interaction and then how we model this. I say it is a simple model because we are not considering the continuity of groundwater storage with respect to the type of flow that takes place. We are looking at it as a box in which the groundwater storage is fluctuating, and similarly we put levels within which the groundwater levels can fluctuate and so on. So, it is a lumped model, it sits in a very large scale, it is a very large scale lump model. You can replace it with any of the distributed models. For example, you can take mod flow and then replace whatever I am saying now with the mod flow. So, you can include as many details as you desire, and such models are readily available. We should be able to plug in those models and then address the problem of conjunctive use. However, the focus here now is how to formulate the problems, given that there is a surface water model, given that there is a groundwater model, you need to put them in a systems model. That is the focus of this lecture now. So, we will take a system like this, where you have a surface reservoir. At the surface reservoir, there is a inflow which is governed by the catchment of the reservoir, the rainfall in the catchment of the reservoir, and then there is an evaporation taking place. There may be also a direct seepage from the reservoir itself. You have a canal release, you may have a canal network here, and this is just a conceptual diagram in which I am showing just one canal, but it is actually a network of canals, and the canal release is made to an irrigated area. there is a seepage that takes place as the water flows from the reservoir to the irrigated area. This is through the canals, and in conjunctive use modeling, perhaps you will allow for some seepage rather than making everything perfectly lined and preventing the seepage, because the idea is also partially recharge the groundwater. So, typically the field channels etcetera you leave unlined, so that there is a seepage that is taking place. So, canal seepage goes as canal recharge, part of it at least goes as canal recharge. Then at the irrigated area you have the rainfall, and then you have excess water going as deep percolation. That is, the water above the field capacity of the soil goes down as deep percolation, and part of this deep percolation will add as recharge. You also have pumping at the ground at the aquifer to supply water to the irrigated area, and part of this pumped water also comes down as deep percolation and then joins the aquifer. At the aquifer, you may have a boundary like this, you may have a net inflow and a net outflow. So, the aquifer will take it as one box and look at the continuity here. Irrigated area, we take it as one box and then look at the soil moisture continuity if desired. Then the surface water reservoir is another box in which we look at the surface water continuity. So, simply put all of these different components together and then look at an optimization problem. What is the problem here? The problem is to decide how much to be released from this reservoir here and how much to be pumped from the aquifer during each intra-season time periods. Now, these time periods can be typically a month, it can be 10-day period, or it can be seasonal time periods. So, you decide on the time period of planning and then you look at the optimal use of surface as well as the groundwater. So, the question that we are asking is, during each of these time periods that you have so decided, how much should be released from the surface water and how much should be released from the groundwater, such that over a period of time the system becomes sustainable, in the sense that you are able to meet all of this demand, yet at the same time you are able to maintain the groundwater levels within those prescribed limits, such that it does not come nearer the surface nor is it overdrafted. That is the idea here. So, the decision variables that I am talking about are the reservoir release during each of the time periods. Now, I am formulating this model, this particular example for monthly time periods. So, we will do the operation for monthly time periods. Remember, this is a planning model where you will plan how much to use from surface water and how much to use from groundwater. The actual operational model, which is the real time operation, will be slightly different, where you will take the input from the planning model and then incorporate in real time. So, right now you look at this as a planning model. That means, how much to be used, how much do we plan to use from surface as well as from groundwater. That is the idea here. So, RT is one of the decision variables, that is reservoir release during time period T, and the groundwater pumping during time period T, GWT. So, I will denote this as GWT. Now, we will say, as a simplest first cut of objective function, we will say that we want to maximize the net benefits in a year. Now, the net benefits need not be always economic benefits, you may have intangible benefits also included in the model, but right now for simplicity we will simply take it as economic benefits accruing out of the water resource systems operation. Which means what? The amount of water that we apply to the irrigated area in every time period T, both from surface water as well as from groundwater, has a benefit associated with it, and this we will assume that we are able to expressed in terms of the economic benefits. So, that is why we say that we would like to maximize the net benefits in a year for this conjunctive use system. Then on this we will have to put the constraints. So, we define the objective function, we define the decision variables. Now, there is a set of constraints that we need to look at. First, we have to look at the groundwater balance, that is from time period to time period. We are taking monthly time periods now. So, starting with first time period, which is the first month, we need to look at groundwater balance, how the groundwater levels are fluctuating, which means we need to look at the initial storage, groundwater storage, to which how much is recharge, how much recharge is added, how much of it is taken out as pumping and how much is lost through other means, which we will discuss presently, and how much is the end of the period storage. So, that is a groundwater balance. Similarly, at the surface water reservoir, you have the surface water balance. The inflow comes in, there is a existing storage and then there is a evaporation taking place, there are other losses through seepage taking place and then you are releasing certain amount of water, there may be spill that is taking place at the surface reservoir, etc. All of this together will govern the surface water balance. Then we may specify the maximum and minimum drawdown. That means, we will specify that the groundwater level, the water table should be within certain band, that is the maximum and minimum water drawdown. Then you may have storage limits at the reservoirs, that is the surface water reservoir. You may specify a dead storage and there is a capacity associated with it. So, the surface storage should be within these limits, that is reservoir storage limits. Then you have the irrigation requirements, because you are operating this particular system for a given cropping pattern and you would like to meet the irrigated agriculture demands, and therefore, you will specify the constraints associated with the demands themselves. That means, every time period you need to meet the demands to the best extent possible. Then apart from specifying the limits for the groundwater level, for the groundwater fluctuation, you may also want to place certain upper limits on total pumping through the year. So, you may specify certain constraints on the groundwater usage by specifying the volume of water that is pumped from the groundwater all through the year, which means every time period there is a decision variable associated with the groundwater pumping. So, you know how much is pumped every time period and you aggregate that, the total pumping that you have decided based on the model should be less than or equal to certain pre-specified amount. So, that is another constraint that you may want to put. So, like this, depending on the type of situation that you get, you may specify different constraints. So, we will take these constraints and then look at how to put it as a optimization model. So, what did we do? We decided the decision variables. We said the decision variables are the release from the reservoir, surface reservoir RT during time period T, and the groundwater pumping during time period T, GWT. These are lumped models. So, we are looking at the total pumping from the ground aquifer and the total release from the reservoir, surface water reservoir. And then we decided on the objective function. We said the objective function is to maximize the net benefits accruing out of the water application at the reservoir, at the irrigated area. So, you are applying the water both from surface source as well as from the ground source. The actual amount of water that is applied at the irrigated area has a net benefit associated with it, and then that is what we want to maximize. And then we decided on a set of constraints, including the groundwater level fluctuations, including the storage that fluctuates between, let us say, dead storage and the maximum storage, including the meeting of the irrigation demand. So, you may want to say that RT must be always greater than or equal to DT, where DT is the demand and RT is the release, and so on. So, this now we will put more formally in a mathematical form and look at how we formulate the different constraints and the objective function. So, first we look at the groundwater balance itself. Remember, we are talking about the groundwater as one box here, in which there is a net inflow and there is a, or there is an inflow and there is an outflow. So, we may have a net outflow from this system, and this has a storage, and we may say that the storage during any time period must be within certain limits, and we assume that we have a model because of the parameters being known. From the storage, we are able to convert the storage information into groundwater level information. So, we will be able to assess both the storage as well as the groundwater level at each of the time periods. Now, how to do this is a different and slightly more involved topic altogether. We will not go into this. For the purpose that we are looking at, namely put it in a systems model, you assume that this is like a box in which the storage is fluctuating much the same way as the surface water reservoir storage fluctuates, and then we will incorporate constraints associated with it. So, what we will do is, we will take this as the change in the storage. There is a net inflow that is coming here, and then there is a outflow that is going out of the system. So, we will take this as the change in the storage. So, we will say volume change in groundwater storage, this is SGW. We will include all the terms that add to the groundwater storage. So, all these positive terms are actually adding to the storage, and all the negative terms indicate how much is extracted because of various reasons from the storage. We will see one by one all of these terms, and then you may have a plus minus term depending on whether it is adding or it is being extracted. So, the left hand side here is the volume change in groundwater storage. So, change in storage. Now, the first term WP is the recharge from precipitation infiltration. As I said, from in the irrigated area, there is a precipitation taking place. The precipitation in excess of the field capacity in the soil, that is the precipitation that is going down into the soil in excess of the field capacity, which is infiltration in excess of the field capacity, goes down as recharge. We will assume that all of that goes down as recharge, although you must remember there is a unsaturated zone, vadose zone, in which the flow also takes place horizontally. So, not all of the seepage or not all of the infiltration comes down as recharge, but for the time being we will assume that all of that comes as recharge. Then you may have recharge from streams, lakes and other natural water bodies, that is WR. Then we have recharge by storage structures, canals, distributaries and other irrigation works. So, this is because of the seepage through the canals and the storage and so on. Then you may have the groundwater inflow. If you are looking at the aquifer boundaries like this, typically what we do is in the conjunctive views models, we look at the irrigated area which is on the surface, and then we demarcate the boundaries of the irrigated area, and then look at the aquifer boundary below the irrigated area. Physically, the aquifer boundaries and the irrigated area boundaries will not match with each other, but for the purpose of conjunctive use, we take only that much area of the aquifer or that boundary of the aquifer which is just below the irrigated area, and therefore, anything outside of that, this is now looked at as a control volume, and then anything outside of that you account for through inflow into that system as well as outflow from the system. So, GWI is this, what is coming into the control volume or the aquifer. Then you have recharge from surface water applied for irrigation. So, this is WAS term. Then WAG is recharge from return circulation of groundwater applied for irrigation. What we meant here is that, as you see, From the surface water, there is a part of thing that is coming down and adding to the aquifer, which is a recharge due to the surface water application. From the groundwater, there is also a recharge that is taking place, and that is return circulation from the pumping. That is what is meant by these two terms. Then you have GWB, which is the groundwater discharge to streams and springs. So, from the within the aquifer, you are also taking out some water, or it is contributing something to the streams as well as the springs. Then you have GWE, which is the groundwater extraction by pumping and flowing wells. So, you have actual pumping or some wells which are just directly flowing into the irrigated area, and then you have the groundwater outflow. So, these are various components. If you want to go into further details, you can also add the ET losses of phreatophytic vegetation. That means, there are vegetations which are directly dependent on the water table itself. They take the water directly from the water table. So, they are called as phreatophytic vegetation. Typically, these have large depths of roots, that means large lengths of roots which extend into the water table itself. Then you may have other terms included depending on the situation. For example, you may have artificial recharge through injection well. Directly it may be recharging into the groundwater, in which case it becomes a positive term. So, like this you identify various terms in the groundwater balance. This is simply the net change in the storage is equal to what has been input minus what has been taken out, that is all. Now, the recharge components that we are talking about, two different recharges now, several recharge in fact. One is directly through the rainfall, another is what is applied on the irrigated area. This comes as infiltration, and whenever the moisture content below the crop is more than the field capacity, the moisture content in excess of the field capacity comes down as deep percolation, and we are assuming that all of the deep percolation goes as recharge. So, the recharge component depends on, first of all, the geology, what type of aquifer that you have. It may be hard rock or it may be alluvial and so on. So, it depends on the geology itself. Then the intensity and duration of rainfall, evapotranspiration, soil moisture, runoff, infiltration capacity, storage characteristics, movement of groundwater in the aquifer, and then the flow in the unsaturated zone, that is the Vadose zone that I just talked about, and so on. So, there are ways of computing the recharge, which generally is based on all of these factors. We will not go into those details, we will simply assume that we know how to compute the recharge for a given data which pertains to all of these amounts. Then at the surface water reservoir, you have the surface water continuity. This is the same continuity that we have been talking about in the reservoir systems. So, we will write the change in storage St plus 1 minus St is equal to, this is the inflow minus RT, which is the decision variable, minus ET, which is the evaporation and all other losses together. So, we will write a simple continuity equation like this. Remember, RT is the decision variable here, ST also becomes decision variable, whereas IT and ET are the data. So, simply what we are doing is, for the surface water storage, as I mentioned, the surface water source need not be always a dam and associated reservoir. It may be simply a tank or several tanks together, irrigation tanks. So, you are looking at irrigation tank and groundwater usage simultaneously or conjunctively. So, essentially we are looking at the inflow that is adding to the storage, there is a seepage that is taking place, you have an outflow and this RT is a decision variable, and then from this evaporation is taking place. So, this decides the continuity or the storage continuity. Now, in this broad framework now, we will take a simple example. I keep repeating simple because the conjunctive use problems are in fact very complex. You need to look at the two-dimensional groundwater model. You may have to incorporate or include the two-dimensional groundwater model into the optimization problem itself. We will come to all those complexities if time permits at the end of this lecture. So, from the drawdown conditions, this is for an example, we will say that the total groundwater that can be pumped in a year is QP. So, we will specify the volume of groundwater as QP. Then whatever is released from the reservoir as it goes through the canal network, 30% of that goes as canal recharge. That means, it goes out as seepage through the canals and then adds to the canal recharge. So, 30% of the release goes as recharge. Then whatever is applied at the irrigated area, 10% of the water applied comes down as recharge. Now, whatever is applied at the irrigated area may come from surface water source as well as from groundwater source or from both these sources together. But whatever is applied, 10% of that water also comes as recharge. Then we have the inflow at the reservoir as IT, and we will say that net benefits for each unit of water applied in period T as BT. We will indicate this as BT. We will assume that monetary returns are known per unit of water applied in every time period. We will denote the groundwater storage in period T by GST. So, this is groundwater storage, and we will specify that the GST should be within certain limits, minimum to maximum. Similarly, at the reservoir, we have the reservoir capacity and the irrigation demands are denoted as DT. So, all of these are data. We know IT is known, DT is known, and QP is fixed. So, all of this is data. This is known, this is known. This becomes a decision, that is GST becomes a decision variable, as indeed is ST, which is the storage at the reservoir. Okay, we will write now the optimization problem. The objective is to maximize the net benefits accruing out of the conjunctive use of surface as well as groundwater. We know that the benefit per unit water applied at the field is BT per unit water, and how much we have actually applied? We have applied GWT, which is the through the groundwater source, and 0.7 RT, which is from the surface water source. Remember, we are talking about the actual application at the field level. So, this is the irrigated area and you are bringing RT here, 30% goes off as recharge. So, what is actually applied here is 0.7 RT, and at the same time you have also applied GWT, which is a groundwater pumping. So, this term here, that is GWT as well as 0.7 RT, GWT plus 0.7 RT will indicate the total amount of water, and for every unit of water that you apply, you have a benefit of BT. Therefore, this gives you the total benefit accruing out of the water application, and this we sum over T is equal to 1 to 12. There are 12 time periods, and therefore, this gives you the total benefit across a year. Then we write the reservoir storage continuity and the groundwater balance. In the groundwater balance, now we have discarded several terms. We will simply take it as GST plus 1, which is the groundwater storage at the beginning of time period T plus 1 is equal to the groundwater storage at the beginning of time period T plus whatever has come from the canal seepage as recharge. We released RT from the reservoir, 0.3 of RT, that is the 30% of RT comes as canal seepage, and that is the recharge. Then whatever is applied at the irrigated area, we applied GWT, which is the pumping from the groundwater, plus 70% of the release RT, and this is the total amount that is applied. 10% of that comes as recharge. So, that adds, and minus GWT. Now, this is the decision variable, GWT is the pumping. So, these are the two major constraints that we need to look at. One is the storage continuity, another is that is the reservoir storage as well as the groundwater balance. Then we put all other conditions that our groundwater storage must be within these two limits. The surface water storage must be less than or equal to S max, and then we put the condition that whatever you apply at the irrigated area, namely the groundwater pumping, groundwater application plus the surface water application must be greater than or equal to the demand itself, dt. And we have also specified that the total pumping in the year must be less than or equal to QP. We have said the QP is the maximum pumping that is allowed in terms of volume. So, every time period, in time period T you have GWT as the pumping. So, the total in the time period is in the year is T is equal to 1 to 12 GWT. This should be less than or equal to QP. For this is not there. So, this is the maximum permissible pumping in a year. And then because you are doing it in a deterministic sense, you will put S13 is equal to S1 and GS13 is equal to GS1 to indicate that end of the period storage is equal to beginning of the storage for next year. And then you also add the non-negativity conditions. So, this is the complete model, although a very simple model. I keep repeating simple because it is all lumped. Groundwater aquifer is lumped, irrigated area is lumped, surface water reservoir including the canal networks, everything is lumped. So, this is the model that we write, and then we will take the example where the data is given like this. You have the inflows in million cubic meters, you have the demands in million cubic meters, you have the evaporation in million cubic meters. And then you also have the net economic returns. So, these are the BT values. Now, the BT values are for several for 12 time periods, these are like this 60, 50 etc. Remember, BT is the net benefit that you get per unit water applied at the irrigated area. Then reservoir capacity is known. Then we also specify volume of water that can be pumped from the aquifer over the year, which is QP. QP is known, and maximum volume of groundwater that is allowed to be pumped in a period. Now, this we may put it as G max, that means GW is our decision on the pumping, but we will say that GWT, which is any period T, the pumping in any period T must be less than or equal to 200 million cubic meters. You should not pump more than this. Then we have taken canal seepage as 30% and recharge due to irrigation as 10%. So, all of these data are known. So, we put this data into this model now. So, this is known, this GWT is being it comes out as decision variable, RT comes out as decision variables, and in this ST comes out as decision variable, RT comes as decision variable, GWT is decision variable, and so on. So, all of the terms that are required to run this model are given now through this data. We use this data and then make the run using a Lingo model. It is a linear programming problem. So, we use Lingo and then obtain the solution. Now, the solution here is it provides how much of groundwater to be used and how much of release to be given from the reservoir. These are all in volume units. And for comparison purpose of seeing how much of the demand is met, we put this term now. This term here is the water applied, actual water applied at the irrigated area, and this is the water demand. And we also look at the recharge that is taking place during different time periods. So, the demand here is not met for several time periods, and there is the recharge that is taking place, so that the demand can be met in the other time periods to the extent possible. Now, you can do several analysis with this. So, this is a type of model, several types of analysis with this. First thing is, you see that there are certain periods in which the demands are not met. For example, this period there is a big deficit, this period there is a big deficit, this period there is a big deficit, and so on, which means that there is a crunch of resource both with groundwater as well as surface water together. There is still a deficit of resource. So, you can start doing a sensitivity analysis, start increasing the reservoir storage and then see how the solution will be. Start increasing the groundwater availability and then see how the storage, how the solution changes and so on. So, typically from such solution you get a idea of what kind of demands that are met. For example, you look at this red line here, this is the demand pattern, and anywhere else which is not seen, it coincides with the green level. Green is demand required. So, wherever red is not seen, it is coinciding with the green, and there are several time periods within this, typically between 2 and 6 months as well as from 8 months to 12 months, the demands are not met to a great extent. Then you will also look at how much of groundwater that is pumped, how much is released from the reservoir, and the demand that is required, and so on. So, you look at all of these. In fact, you can also put the recharge, what kind of recharge that is taking place and so on. Now, on this you can do several sensitivity analysis to see how sensitive is the solution with the reservoir capacity K. You try increasing the reservoir capacity K, but you will very soon realize that this solution may become insensitive to reservoir capacity itself, because it may be limited by the inflows. If your inflows themselves are small, then no matter how large a dam you build, you may still be not able to meet the demand, and therefore, you may have to start increasing the groundwater that is available, but the groundwater will be limited by the actual aquifer conditions. Therefore, you may not be physically able to increase the storage beyond a certain point. So, this is how you model the conjunctive use of surface as well as groundwater, and this is a simplest model. You can also include a two-dimensional unsteady flow for the groundwater flow itself. In this example that I just discussed, what we did was that we took it as a lumped model. However, you can go into two-dimensional unsteady flow model and write a finite element code for this, convert this differential equation into a finite element numerical method, and then at each element you write the continuity equation. So, these type of complex models are available in literature, you can just go through it, but the broad philosophy of the systems model remains to be broadly what I have discussed here, namely that you identify a objective function, write constraints associated with the groundwater, write constraints associated with the surface water, and so on. Now, if you want to put a finite element model for the groundwater, then all of these constraints that I have written must be written for each of the element. Typically, we may write a element to be choose a element of size 2 km by 2 kilometers, and then write the constraints for each of the 2 kilometer grid, and it will also depend on the soil moisture balance. It may depend also on the soil moisture balance at each of these nodes, the elements that you have written 2 kilometer by 2 kilometer, and then the mesh type that you choose for the finite element and so on. But such complex models are in fact available, and then on top of that you can also include the uncertainties associated with the inflow, the rainfall, the evapotranspiration and so on. You can build stochastic models for conjunctive use of surface and groundwater, but broadly the philosophy remains the same. So, in today's lecture then we have just discussed the conjunctive use model. We will continue the discussion in the next class, where we introduce another type of model formulation, not for conjunctive use. We will look at certain case studies and so on. Thank you for your attention.